Now in this last figure, we're going to do the same thing where we're looking for the electric potential, but using our super cool new tool here. And this one we have a charged disc that has a surface charge density, area charge density of sigma, and it's conveniently placed. The point that we're evaluating the electric field is perfectly over the center of the disk, who has a radius of r, and that point is situated distance z above the center point. So again, we'll substitute lambda in for our charge density here and start wielding this new tool that we discovered. And again, this is only 4 points that are for reference points for the electric potential from infinity. So 2 pi r, and then of course our we're going to integrate from 0 all the way out to r, and we have the 2 pi r here because we are sweeping across. So we'll take a chunk of charge density here, sweep it across, evaluate it all, and then move out to the next one, sweep it across, move it out to the next one. You know, your standard calculus craziness. The distance, the most arbitrary distance is some point r away, and then z remains constant. So this is what we are using as the arbitrary distance for our separation vector, and that's by that Pythagorean's theorem. It's z squared plus the arbitrary r squared, the arbitrary distance. So all right, and then we're going to evaluate from dr. All right, so we'll go ahead and start chugging along this integral. We can pull out all of this, not the r, but that. And what we're left with is let's see here. Let's clean it up. Sigma 2 pi over 4 pi epsilon naught. Gonna need to clean that up later. And the integral, what's left is r over square root of all that stuff under there. And that's one you're gonna want to know in the back of your pocket. Is it's just gonna be what's under the square root evaluated at the two limits. So from 0 to r, 0 being what I'm writing right now. I'm sorry, z squared. Right? So yeah, evaluating from r is from r squared to z squared, or 0 squared. Makes things a little bit easier. Before I move on, let me do some cleaning up here. This ends up being a 2. So let's see here, sigma over 2 epsilon naught. Looks familiar. Kind of like the infinite plane stuff that we've used before. Although this isn't necessarily infinite plane. I think if we pushed the limits out to infinity, we would eventually get to something like that, or we could figure something out. But for right now, this is what we're landing at for our electric potential right here. So a lot faster than setting up the other way. Again, if you're so inclined, you can definitely try it out the original way where we were dotting the electric field. And it would take a while, but we'll just stick with now. It's good to have all these different approach in your quiver as you move on in your physics career. Okay, so what I'm doing now, I just kind of skipped this step. You know that there's going to be an x and a y hat component that ends up being 0 because we only have this in respect to z right now. Or sorry, well actually there'd be like a theta direction as well, since we're working in a now cylindrical world. But either way, all that's left is z, right? And so we're just going to take the negative gradient in terms of z, which is just the negative partial in respect to z. Again, to save time, I'm just going to copy and paste this. There we go. In bracket, tack on a direction, because that's what gradients do. Let's see here. So this kind of floats in, moves in, and gets distributes, and it attacks the z components. So these constants are left unscathed. What we're left with now is, let's see here, bracket, we got a 1/2 chain rule happens to z over r squared. squared plus z squared. That is a tiny one. I'm sorry about that, guys. And then minus 1 in the z hat direction. Let's clean up. So all that's left now is the sigma 2 pi epsilon naught. I think it's safe to use a parentheses now. There's a minus sign. So I'm just going to take that minus sign, distribute into these brackets, which flips the signs of those. So we have a 1, positive 1 minus z over r squared plus z squared, living under a square root, all pointing in the z hat direction. If you go back to the problem, you'll find the original problem referenced in this problem we're working. We'll notice that is actually in accordance with that problem as well. And the last part of this problem actually tells us to go back up and look at this charge distribution that we originally had, right? And think about if we took this one and we turn this into a negative. Let me use blue here. And if we turn this into a negative, right, what would happen? What happens to the potential? Well, I mean, if we look here and we're summing up all of the charge densities, if we have a positive and equal opposite negative one, then our potential, the potential here is going to be equal to 0 at that point, at this point. So evaluate it at P, right? So what does that tell us, right? So does that tell us that the electric field at that point is 0? Yeah, but in terms of the potential of everything else around it, that doesn't necessarily tell us the full picture because we're talking about doing the potential on a line of symmetry here, right? Everywhere on this line of symmetry that potential is going to be equal to 0. However, that's not necessarily true here or here whenever we don't have that symmetry. And if the qualitativeness doesn't help out, you can go ahead and work it out. Just picking an arbitrary point, you'll see that the potential is not necessarily 0 at this point. So by turning this into a negative sign, that doesn't necessarily make all the potentials everywhere in space equal to 0. That just means at this specific point, at this line of symmetry here, that means that the potential equals 0. And then it doesn't give you a full picture of everywhere else. So it's that the questions that the author told us to consider at the end of the problem is just for us to consider. Remember that this is a very useful tool because it's really easy to find and quick to find the potential, but we need to be cautious where we use it. If we try to go anywhere outside of these nice lines of potential and then coming out from infinity into those nice lines of symmetry as well. So that was the main point of that last question of the problem. Again, a lot of questions in this problem.